Section 2.3 is about polynomial functions and their graphs. First of all, what is a polynomial function? Well, a polynomial function is any function that is made up of a series of terms, and we list them from the highest degree to the lowest. So things like 3x squared plus 2x plus 1, something like 7x to the 5th minus 3x cubed plus 2x. Even 3x is a polynomial function. A couple of examples of things that are not polynomial functions. Let's do a couple here. Let's say f of x equals x cubed minus root 2x. This is a polynomial function. Root 2 here is simply a coefficient. It's a number just like any other. I could also rewrite a polynomial function in factored form, something like this. If this were to be expanded, this would be a series of terms. That's a polynomial function. Something like this, however, for root x plus 3, this is not a polynomial function. The power for the x value has to be a whole number. This would be x to the 1/2. That's not a polynomial. Another example of one that would not be would be something like this. Something raised to a negative power is also not going to be a polynomial function. So there's some examples of functions that are and are not polynomial functions. Every polynomial function is smooth and continuous. That means that when we do a graph, it's going to be something like this. And it's going to always be continuous. It's always going to be smooth. It's not going to have any peaks like this. It's not going to have any breaks in the graph like this would. So polynomial functions are smooth and continuous. One of the things that we look at to help us graph polynomial functions is their end behavior. And on page 3 or 4 in your text, there is a little chart about end behavior. What we're talking about here is what happens as what happens as x approaches infinity or as x approaches negative infinity. In other words, on the graph, what happens way out here to the right and way out here to the left. And the end behavior refers to whether or not the graph, or whether f of x goes up or down as x goes out to the right or to the left. Now, some end behavior you already know. Linear functions, like 3x plus 1. You should know that this graph, and I'll draw it over here just to see, goes up towards the right and down towards the left. So, for this linear function, as x goes towards infinity as we move to the right, f of x, the y value, goes up, which is also positive infinity. So as x moves towards the right, the y value goes up. As x goes towards infinity, y goes towards infinity. As x goes towards negative infinity, as the graph, I want to write that this went right up here. As the graph goes towards the left, then f of x, the function, goes down or towards negative infinity as well. So here we have, as x goes towards infinity, which is to the right, f of x also goes to the right. Now what happens to this graph as I change this and make the leading coefficient negative? Hopefully we remember that if we have something like f of x equals negative x plus 3, Now we're going to go up to 3, and we're going to go this way. Now, as x goes towards infinity, f of x goes towards negative infinity. In other words, as x goes to the right towards infinity, f of x, the function value, the y value, goes down. And as x goes towards negative infinity, as the graph moves towards the left, the function value goes up. This is called end behavior. So we've done it for a linear equation where it's x to the first power. Let's take a look at what happens when we are dealing with a squared function. So if we have y equals x squared plus 3, that looks like this. It's a polynomial that is a quadratic. Now, as x goes towards infinity, f of x goes towards positive infinity as well. So as x moves to the right, f of x goes up. As x goes towards the left, towards negative infinity, as we're heading in this direction, what happens to f of x now? Well, it still is going up, so it's going towards infinity. So as x goes towards the right, f of x goes up. As x goes towards the left, f of x goes up as well. Okay, let's look at our other scenario. What happens if we have negative x squared? Well, now, no matter what happens to x, as x goes towards infinity, the function goes towards negative infinity. As x goes towards negative infinity, the function also goes towards negative infinity. So let's see if we can generalize this. When we have an odd-powered function, all odd powers, whether it be x or x cubed or x to the fifth, and remember we're talking about the leading term here. If a, the leading coefficient, is greater than 1, it will always, or excuse me, greater than 0, it will always go up on the right, down on the left. If a is less than 0, it will go down on the right and up on the left. Now, depending upon the power, this might be a straight line. It might be something that has some loops in it. We don't know. All we really care about here is what happens at the end of the graph. Even powers act like a parabola. X squared, x to the fourth, x to the sixth, etc. Here, if the leading coefficient is greater than 0, both ends go up. And here, if the leading coefficient is less than 0, both ends go down. Again, we don't know what happens in between. It could be a lot of things, or it could just be a single loop. But the end behavior is what we're concerned about. So anything with an odd-powered leading coefficient acts like a line, one side up, one side down. Anything with even powers acts like a parabola, both sides up or both sides down. So that's our end behavior. The next thing we want to look at are what's called multiplicities of 0. And there's a nice little definition on page 306, so you might want to pause and write that down. But the bottom line is, what is going to happen when we are looking for zeros? Now remember, zeros is another word for x-intercepts. So let's look at an equation, y equals x plus 1 times x minus 3. Now to find the x-intercepts, remember we set y equal to 0. So here's my function. It's already factored for me. That's very nice. So I find out that my zeros, or my x-intercepts, are -1 and 3. And we know before from experience that this is a parabola. Intercepts at -1 and 3. This is going to have a positive leading coefficient, understood to be 1 here. so it's going to have end behavior that goes up on both ends. So there's my graph, and you can see that at my zeros I cross the x-axis. Now when we have multiplicity of zeros, different things may happen at these x-intercepts. So let's take another example. If I have this function, x minus 3 squared, my zeros are x minus 3, x equals 3 and x equals 3, that means it only is going to touch the x-axis at one point. Now, how is that going to work since this is a parabola? Well, let's see what this equals. This equals x squared minus 6x plus 9. It has two x-intercepts, but they are the same. In other words, this 0 repeats 2 times. This must open up. It must be a parabola. So what we have is a 0 that touches and turns around rather than passing through the graph like my others did. Let's take a look at another one with your graphing calculator. Pull out your graphing calculator and plug this equation in and take a look at your graph. Okay, so by looking at this equation, we can see that it is a cubic function. Can you find the zeros? Well, we can do it one of two ways. You can use your calculator, or we could factor this, and I find that I have several zeros. I have 3 factors, and my zeros are positive 1, negative 1, and negative 3. Let's look at this on a piece of graph paper here. So I've got positive 3, positive 1, and negative 1. This is a cubic function with a positive a value, so it should go up on the right and down on the left. So I'm going to go through this 0, through this 0, and through this 0. So here's the deal. When we have a 0 that only appears one time, the graph passes right through that 0 and goes to the other side. Passes through again, passes through again, just like it did on my original parabola. If a 0 appears 2 times, if it repeats, then the function will simply touch and turn at that point. So let's see if we can recap this. If a 0 appears an even number of times, in other words, it repeats 2, 4, or 6, and it's the same 0 every time, then the graph is going to touch at this point and turn around. If a 0 appears only once, whoops, can't spell. If the 0 appears only once, the graph passes through the 0. The one situation we haven't looked at is if a 0 appears an odd number of times, for example 3 or 5 or 7, now it's going to pass through, but it flattens out. Let me show you what that means. So if this is a 0 that has appeared 3 times, let's say we have the function x plus 1 cubed, so that's negative 1 3 times. Whoops, that should have been negative 1, sorry. Now the graph is going to come down. It's got to have end behavior up on the left, down on the right, up on the right, down on the left. But when it comes through, instead of going through like a straight line, it's going to come up from the bottom, flatten out, and pass through. So these are the three situations. They are recapped on page 306 for you. And that's what happens with multiplicity of zeros. What we're doing is we're building a repertoire of things that will help us to graph a polynomial function. Let's try that. Let's look at this function. F of x equals negative 4, parentheses, x plus 1/2 squared, x minus 5 cubed. Now, I know that my zeros, because if I set each of these factors equal to 0, I will have zeros of negative 1/2, which appears 2 times. That's a touch and turn. And a 0 of 5, which appears 3 times. That's a pass through, but flatten out. This is a 5th degree, because those are going to be multiplied together. 5th degree means that it's going to be either up on the right and down on the left, or up on the left and down on the right. Since this is a negative, this is the scenario I'm looking at. So let's do our graph. Negative 1/2, 1, 2, 3, 4, 5. Those are my zeros. I know that it's going to go up on the left and down on the right. This negative 1/2 appears 2 times, so that's got to be a touch and turn. The 5 is 3 times, so it's got to flatten out and pass through, and there's my down on the right. Now this is just a rough sketch. I don't know exactly what happens in between. It might be much steeper. It might do something like this. Okay? It might do something like this. But I do know that at this point it's going to touch and turn. At this point it's going to flatten out and then go through, and it's going to be up on the left, down on the right. So when you're asked to do these sketches, they are going to be rough sketches. It's going to be impossible to tell what happens in between the zeros. But we do have enough information to get us a pretty good graph here. A few other things that will help us out. One is the intermediate value theorem. Let f, whoops, typo there, let f be a polynomial function with real coefficients if f of a and f of b, and remember these are y values, y sub 1 and y sub 2, have opposite signs, one positive, one negative. Then there is at least one value of c between a and b, these are my x's, for which f of c equals 0. Let's break this down. So if I have a point a, f of a, and another point b, f of b. If f of a and f of b have opposite signs, in other words, one is above the x-axis and one is below, then somewhere between a and b there has to be a value c where f of c equals 0. And this is really just a complex way of making a common sense statement. For a polynomial function which must be smooth and continuous, if it's got a point above and another point below the x-axis, then somewhere in between it's got to cross the x-axis. So we can use that information when we graph as well. For example, you might be asked to show that f of x equals x squared minus 2x minus 5 has a real 0 between 2 and 3. Well, let's check it out. Let's find f of 2. That would be 2 squared minus 2 times 2 minus 5, which would be negative 5. And f of 3, which would be 3 squared minus 2 times 3 minus 5. That's 9 minus 6, and that would be negative 2. I can say that this does not necessarily have a 0 because both of these are below the x-axis. Let's change this and say, what about between 2 and 5? So f of 5 would be 25 minus 10 minus 5, and that would be 10. Now I can say that between f of 2 and f of 5 there must be a real 0. F of 2 is at negative 5, f of 5 is at 10. Somewhere between these there must be some value c for which f of c is 0. Okay, the last thing that we want to look at is turning points, and that's the place where a graph turns around. So that would be a turning point. This would be a turning point. If f is a polynomial function of degree n, then f has at most n minus 1 turning points. So for example, if f of x is x squared plus 3x plus 1, that is a degree of 2, then f of x has at most 2 minus 1 or 1 turning point. And that should make sense. A second degree is a parabola that has 1 turning point. So whatever the degree is, it has 1 less turn in it. If f of x is x cubed plus 7x plus x squared plus 3x, this would have at most, since it's third degree, 2 turning points. And I can tell you the cubic functions, whoops, I'll make that a negative so my end behavior is right. A negative goes down on the right, up on the left, and it would have 2 turning points. Take a look at page 310. I know we've done a lot, but we're going to do an example together, and then we can work that through. This is the strategy for creating a polynomial function graph, and they've given you that long explanation for a polynomial function. All that really means is line the terms up from highest to lowest. So first they suggest that you use the leading coefficient to find the graph's end behavior. Then find x-intercepts if possible. Pay attention to the multiplicity of your x-intercepts. 3. Find the y-intercept. If possible, use symmetry. This is the least helpful, but an even function, if you remember, even function spins around the y-axis. Odd functions are symmetrical around the origin. And the last thing is to use the turning points. So let's take a look at a function, and this is shown in your book as well. X to the 4th minus 2x squared plus 1. First thing we want to do is end behavior, and this is a 4th degree. That means either both ends up or both ends down. Since a is greater than 0, the end behavior is going to be both ends up. Let's see if we can find any x-intercepts. This does factor x squared minus 1 times x squared minus 1. Whoops, I'm sorry, x squared. Oh, that's not right. X squared. Wait, did I copy it? No, that's right, that's right. And then those are x minus 1 times x plus 1 and x minus 1 times x plus 1. So I have zeros of -1, which appears twice, and +1, which appears twice. So let's see what we've got so far. -1, +1, end behavior up and up. Let's see if we can find the y-intercept. So f of 0 is 0 minus 0 plus 1. And now, knowing that both of these zeros have to be a touch and turn, we should have enough to do our graph. Didn't really need symmetry, but everything else worked well. And the turning points, let's check. If it's a 4th degree, at most it should have 3 turns. It can't have 4. So 1 turn, 2 turns, 3 turns. Perfect. We will do a few more of these in class. Take another look at the examples, and as I said, we'll work on one of these together in class before I let you loose on your own. And that's it.